So till now the focus of the course has been on trying to find efficient algorithms, but sometimes efficient algorithms do not exist. So how do you work in that situation to show that something cannot be done efficiently? So this is the realm of what's called intractability. So we will look at intractability. So we will begin by looking at something called checking algorithms. So when we look at efficient problems for which we have reasonably efficient algorithms, so we looked at shortest paths, minimum cost spanning trees, maximum flow. Okay. By efficient we typically mean that they have these polynomial time algorithms. So polynomial time is generically taken as a definition of efficient solution, although we have seen that even in polynomial time, if you have something that runs in n cubed versus something that runs in n log n, right, there is a huge practical difference in what size problem you can solve with one rather than the other. But from a more abstract perspective of algorithms, anything which is of the form polynomial n to the power k for some fixed k is considered to be good. So now we have efficient algorithms. What do these efficient algorithms do? Well, they actually find a solution from a large set of possible solutions, right? So if you are looking for the shortest path, there are many paths, and we said in general there are exponentially many paths. The same way there are exponentially many spanning trees. Maximum flow also, we said if you are not careful, the Ford-Fulkerson algorithm will do something which is going to be proportional to the size of the actual flow, right? So what these algorithms manage to do is somehow prune this search and find the correct solution without actually examining all these exponentially many solutions, right? So there is some clever way in which you cut through this exponential. But there is always the brute force possibility, right? So the brute force possibility just says enumerate every possible path, every possible spanning tree, right? And then check whether or not that is the best one, or find the minimum or the maximum across all of these. So now this is in general going to be very inefficient. It will be correct because you are explicitly enumerating every possible solution and picking the best one, but it's not going to be computationally tractable. So the question, as I said, is, can we always do this, right? Can we always somehow bypass this exponential search by finding a clever algorithm? So do all problems admit such efficient solutions which bypass this? And unfortunately this is not the case, right? So we will see that there is a large class of problems, and these problems are very natural. They are problems which actually arise in the day-to-day things that we have to deal with, and therefore it's a bit challenging that none of them is known to have a theoretically efficient algorithm of the same type that we have seen here for shortest paths and so on. So let's look at a general question, which is the problem of solving something versus checking that a solution is correct, right? The problem of generating a solution versus checking a solution. So supposing as a maths teacher, I assign you some homework. So I give you a large number which I know is the product of two primes, right? It's a product of two large primes, and I tell you find these prime numbers. So as a student, right, you are given this large number n, and you have to find these primes p and q such that p times q equal to n, and you can imagine that this will be complicated because you have to search for these large primes, because assuming they are really large, you have to go through all the primes up to p in order to find them, right? So in fact there is no known way to do this efficiently. So this is the student's problem. The student's problem is to generate a solution, and it could take arbitrarily long depending on how much time the student is willing to spend on it and how careful the student is about calculations. Now the student submits the homework and I have to correct it. So what do I have to do? Well, as a teacher, the student gives me a p and a q. I am not really interested maybe in how the student arrived at p and a q, I just want to check if it's correct. So if I want to check it's correct, I don't have to do any searching for p and q. I have given p and q and I know the target. I need that p and q is factors of n, and I know that they must multiply to n. So I just multiply p by q, which is a relatively simple procedure, check if it's equal to n. So as a teacher, my goal is only to check the answer. As a student, the person who is assigned this problem, the goal is to find the answer, and it seems intuitive that generating a solution is harder than checking a solution. So this example leads us to the notion of a checking algorithm. So I am given a problem p, right, which I want to solve, and I want to talk about a checking algorithm for that problem rather than a solution for the problem. I want to talk about what would be a checking algorithm. So a checking algorithm like here will take a solution, right? So the student has already solved the problem. So the checking algorithm only has to validate this solution. So it takes the input, so it will take n in this case, right? it will take the input and it will take the certificate, that is the solution which is supposed to be the correct one. In this case, it will be P and Q. And then you check whether the certificate, the solution that the student has given you, is correct for that given input or not. So you have to validate whether that solution is correct. So in our situation, right, the input instance is the number, the large product that you need to factorize. The solution that student presents, the certificate, is the set of factors, and checking consists of multiplying these two factors and validating they actually multiply to the number you started with. So this is a checking algorithm. So let's look at a problem now which is very central to this whole notion of intractability. It's called Boolean satisfiability. So as you know from programming, a Boolean variable is something that can take values true and false, and we know that we can take Boolean values and we can operate on them. So we can negate them, for instance, true becomes false, false becomes true. We can take the disjunction x or y is true if either x is true or y is true or both. So at least one of them must be true, and x and y, which says that both of them are true. If either of them is false, the answer is false. Right? So in logical notation, this is conventional to write it. So you use this symbol for not, this V symbol for or, and this inverted V symbol for and. So we will use these to write formulas. So what we have in Boolean satisfiability is we have such a formula, but the formula consists of variables. So we have some x1 or not x2 or x3 and so on. But this is in a particular form, right? The particular form is that I have only ORs here, right? And the not is attached to one of the xi's. So the xi's are variables. So each of these xi's is an individual value, right? So these are called literals. So a literal is either a variable or the negation of a variable, like not x2 or not x4, right? So x3. So these are all the literals. So a clause consists of literals which are connected by or. It's a disjunction of literals, right? So each part of the clause can be an x or a not x, and they're connected by or. And now a formula will be something which is a collection of these clauses connected by and. So it will be C1, which is a clause of this form, and C2, which is another clause of this form, and C3. So in order for this formula to be true, we need that this whole clause must evaluate to true, this whole clause must evaluate to true, and so on. But within a clause, because we have disjunction, right, it is enough for any one of those xi's within the clause to be true. So that is the challenge now. Which xi's should I make true so that all the clauses become true? So this is called the satisfiability problem, right? So I need to assign values to each of the variables. So every variable xi should be assigned either true or false. Once I assign the value true or the value false, then for instance, I can evaluate the formula and check whether this particular assignment of true or false makes the formula true. If it does, then it's supposed to be a satisfiable assignment, right? So satisfiability says find an assignment that makes the formula true. So if I take this particular example here, so there are three variables x1, x2, x3, right? Now I want to make this true. So there could be many different strategies. You could say greedily, for instance, I need to make each of these clauses true, right? So if I greedily start, I can say that maybe I make this one true. So maybe I should make x1 to be true, and that will guarantee that the first clause is true. If the first clause is, if x1 is true, then this clause also has x1, so this is also true, right? So these two clauses have both become true because I have decided to make x1 true. But I have not said anything about x2 and x3, so I don't know anything about this one. So let's say I want to now proceed to make that true. So then my next step in this kind of greedy heuristic search could be, okay, let me take the next value which I have not yet set to true and make that true. So now I have set x2 to be true. Now I come to the third clause and I find that, oh, x1 is true, so this is going to be false. x2 was also true, so this is also going to be false. So I have, because of my previous choices for x1 and x2, I have already fixed in some sense that two of these literals in this clause are false. So the only way to make the whole clause true is to make this part true, which means I must set x3 to be false, right? So using this kind of a, this is not an algorithm, it's just a guessing game, right? I have shown you that if I make x1 true and x2 true and x3 false, then this formula will actually evaluate to true. So this formula is satisfiable. Now I can add one clause to that, right. So, I am taking the same formula and I add one more clause which says x3 or not x1. Right. Now, you can see that this particular assignment no longer satisfies this, because I have, thanks to this is false, x3 is false, and thanks to this not x1 is also false. So, this particular clause is not satisfied by the assignment which I found for the original formula. And you can reason about why this is not going to work in general, because if I want to make this formula true, then you can work backwards. So, I am not going to prove it to you, but you can check for yourself that if I make x3 true here, then this is going to become false. Right? And if this becomes false and you work backwards, so this is true here, so this is going to become false. Right? So, if this is false, then this must be true, I have no choice. Right? If this is true, then this is false. And if this is false, then this must be true. So, now look at what we have. Right? x3 was taken to be true because I was forced to make something here. So, this became false, not x3. So, x3 I have set to true, so not x3 becomes false. x2 became true, so not x2 becomes false. And x1 had to become true, so not x1 becomes false. So, in the process of setting the red clause to be true, I have ended up making the last clause false. Right? And you can check that there is no way to make this true by just exhaustively checking. So, one way to do it is there are 3 variables, you check all possible 8 combinations, right, of setting x1 to be true or false, x2 to be true or false, x3 to be true or false, and none of them will work. So, this is a formula which has become unsatisfiable. Right? There is no satisfying assignment. So, this is the Boolean satisfiability question. Basically says, I give you a formula in this particular form, right? I give you clauses where inside a clause I have literals with disjunctions, and then I give you these clauses connected by ands, and then your question is to answer is whether there is an assignment to these variables which makes these clauses true or not. So, now if I have to generate a solution, as we said, we can always try every possible assignment, right? We can take an assignment V, which, or a valuation as it is called, which assigns true or false to x1, true or false to x2, and so on. And if there are n variables, then there are 2 choices for each variable. So, 2 times 2 times 2 n times is 2 to the power n. So, I have an exponential number of different valuations which can arise. So, the question is, can I do better, right? So, this was the whole idea of having efficient algorithms, that there is an exponential search space, but there is a clever way of cutting through that exponential search space and finding the assignment or not finding the assignment quickly. Unfortunately, we do not know. Right? So, this is literally the situation with Boolean satisfiability, that we have no idea whether there is an algorithm which is guaranteed to find this satisfying assignment without exploring all these 2 to the n possible assignments. In some cases it may work, but whether there is something that works for all such formulas, we do not know. On the other hand, it clearly has a very efficient checking algorithm, because a checking algorithm will take a solution. So, what is a solution? A solution is the form what we saw before. It will say x1 is true, x2 is true, x3 is false. So, this is my candidate solution. So, what you have to do is then plug in these values in the formula and then evaluate, because you know what OR means, you know what NOT means, you know what AND means. So, if you substitute explicit true, false for each of the variables according to the valuation, you can evaluate the formula explicitly, quickly in linear time, and tell me whether the formula is actually true under this valuation. So, whether this is a real satisfying valuation or not. So, checking is efficient, generating appears to be not efficient. Now, as I said before, it does not mean that no Boolean formula can be solved, right. So, we have taken this particular form where we have these clauses consisting of disjunction of literals, and we combine these clauses using AND, right. So, this is a particular form called conjunctive normal form. But what if we reversed it? Supposing we construct these clauses using AND, and we connect the clauses using OR. So, that is the opposite, right. So, we are now, earlier we had OR inside the clause and AND connecting the clauses. Now, we have AND inside the clause and we have OR outside the clauses, right. So, we write it as C1 or C2 or C2. Now, the problem becomes very easy, because if this is a clause, I can check whether this is true or not by just walking down and saying, okay, this says everything has to be correct, right. So, this forces me to set T1, x1 to be true, it forces me to set x2 to be false, it forces me to set x3 to be true, and so on, right. So, each clause forces a valuation to make that clause true, and I have to make one of the clauses true, right. So, each clause forces a unique valuation. So, I check whether the moment I find a clause which is satisfiable by that fixed valuation that that clause is enforcing, because it is the AND of some literals. So, it is saying these literals must have these values, otherwise this AND will not be true. If that is possible, if there is no contradiction inside the clause, right, if I write inside a clause, if I write x1 and not x1 and something, then clearly that clause is not going to be satisfiable, right. But otherwise, I'm going to be able to find one in general. So once I find that, I'm done, because if I can satisfy C1, I don't care about the rest, because it's only an OR. The moment I can satisfy one clause, the whole disjunction is satisfiable. So this becomes much easier, right? I can just try C1, that involves fixing a valuation by looking at all the literals in C1 and checking if that makes C1 true. If it's true, I'm done. If I cannot find such a valuation, if that C1 has a contradiction, I move to C2. So in one scan, I can fix the valuation and check whether this valuation works or not. So therefore, it's important that the satisfiability problem is stated the way we stated it, which is that we have ORs here, right, and we have ANDs here. Otherwise, it becomes a trivial problem computationally. Okay, so that's called conjunctive normal form. Now, let's look at a very different problem, right? So let's look at a problem which you may have heard of called the traveling salesman problem. So this is a variation of our many shortest paths problem. So a traveling salesman problem consists of a network of cities, and there is a distance between each pair of cities. Now you can go from anywhere to anywhere. So you can think of this as a complete graph, right? So for every pair of cities, there is a way of going directly from one city to another by paying some cost or some time or some distance. So our goal is to find the shortest tour for the salesman that visits every city exactly once, right? So a tour is something which is just a cycle, right, which starts at some city, visits every city and comes back. It should be a simple cycle. I am not allowed to visit the same city twice, right? It must visit all the vertices, so every vertex must appear in the cycle. And among all such cycles, it must be of minimum cost, right? Now clearly there are cycles because it's a complete graph, right? So I can find many cycles, so there is no problem of finding cycles. But the problem is to find the minimum cost cycle. So this looks clearly like a difficult problem to solve because there are exponentially many cycles and I have to search through all of them. But let's look at the checking part of it. Supposing somebody claims to have solved this problem, how would we validate that thing? So how can we design a checking algorithm for this problem? So remember that a checking algorithm must take a solution and say yes or no, right? So here, what would be a solution? A solution would be a cycle like this, right? Somebody will say, here is my cycle, this is my tour for the traveling salesman, and it is the best tour that the traveling salesman can take. So what can we do? We can verify that it's a simple cycle and that it visits all the vertices, right? So that is easy because that's just a graph theoretic property of that thing. We just have to check that every node is connected to the next node, every node appears there, and no node except the starting and the ending point appear twice, right? Everything else appears only once. So that's easy. And of course, by looking at the edges involved in this, I look at xi plus 1 in this particular sequence, I can get the edge weight from the graph and I can add it up. So I can find the cost. But I need to find the minimum cost, right? So how do I validate that this cost is the minimum among all the cycles? Because I don't have a reference for that solution, right? So how do I check that it's the least cost cycle? So there is that bottleneck now for this problem. To convert it into a checking problem, I don't have a way of validating the numerical answer that I'm going to get. I can validate the structure of the answer, that it is a cycle that visits all the cities. I can compute the numerical cost of this answer, but whether it's minimum or not is something that is not obvious. So the way you get around this, right, is to ask a question slightly differently. So you transform the problem and say, is there a tour for the salesman with a budget of k, right? So imagine that those costs represent some ticket costs of traveling between the two cities. So you have a total budget of k to buy tickets. So can you achieve a traveling salesman tour with a budget of k? Now the problem is easy because I can check it by finding out if there is a solution and verifying if the cost of that solution is within k, right? I'm not asking whether this k is minimum or not. I'm just saying, is the cost within budget? Now how do I solve the original problem? Well, I try different k's, right? And how do I find different k's? Well, I need to start with some value, so I need to have a bound on the k's. But there is a kind of very easy upper bound if I add up the cost of all the edges in the graph. Now you know that the traveling salesman tour is going to take some n edges, right? It's going to connect n vertices in a cycle. So I'm going to have n edges going from the first to the second to the third to the nth and back to the first one. So the sum of these n edges cannot exceed the sum of the weights of all the edges in the graph. So if I just add up the entire edge weight of the graph, I get an upper bound. So my k that I want to achieve, the minimum cost, is somewhere between 0 and that maximum. So I can start with the maximum by 2, right, and I can say is it achievable. If it is achievable, then I will say can I achieve something smaller. If it is not achievable, then I need to achieve something bigger. So I can do a binary search, right. I can say if my overall things adds up to 1000, then I can say is it achievable with a cost of 500. If the answer is yes, then I will say is it achievable with 250. If the answer is no, then I need to go above 500, so I look at 750, right. So I just do the usual binary search. So I can find the optimum k by doing a logarithmic number of searches, right. So assuming that somebody is there who is going to produce an answer for me, I can do a logarithmic number of checks to find the solution that works. So here is another problem, right. This problem is called independent set. So we say that two edges are independent if they are not connected by an edge. For example, two vertices. So for example, 1 and 4 are independent because there is no edge connecting 1 and 4. So an independent set is a set where all the vertices are independent. So for example, supposing I take 1, 4 and 5, then there is no edge between any pair of these, right. 1 and 4 are not connected, 4 and 5 are not connected, 1 and 5 are not connected. So this is an independent set, right, then nothing in there which connects each other. So this is the basis of many interesting problems that you might solve. So for instance, supposing these are people and you want to form a committee, but you don't want to have a committee in which friends collaborate to achieve some outcome. So you want to make sure that the committee consists of people who don't know each other well, so that they will come up with a neutral solution and they won't have any bias. So you would like to find, so these edges now represent friendship, and you would like to find a committee in which no two people are friends. So that is an independent set, and the largest such typical thing is what we want to find. So we want to usually find the largest independent set in a given graph. So here for instance, this collection 3, 4, 5 is an independent size 3, and it turns out this is the largest set. We also saw another one like 1, 4, 5. So there may be more than one, but we want to find out the size of the largest independent set. So this is a standard graph theoretic problem. Again, there is no easy way to solve this apparently, except to look at, first of all, you have to identify all the independent sets and try to find the largest one. So now if you want to check this, right, if I give you a set of vertices, you can certainly validate that it's an independent set, because you can check that no two vertices in that thing form an edge. But how do you check that it's minimum? Well, where you have to have a budget, just like for the traveling salesman problem. I have to ask you, is this a minimum, is this an independent set whose size is at most k, right? So then if it is k, it's fine and independent, otherwise you say no. So there is a dual problem called vertex cover. So in independent set we were looking for pairs of vertices which are not connected by an edge. Here I am looking at vertices which connect to all the edges, right? So if I look at this vertex 2 for instance, right, then it covers all these edges which are adjacent to 2, right. So anything which is incident to 2 is covered by 2. So node u covers every edge uv which is incident to u. So what we want is a vertex cover. So a vertex cover is something which has a collection of vertices cover all edges. So for instance, if I take this one, then I will get these edges, right. So now I have a few edges which are missed out. So I could, for instance, want to cover this edge, I could take this vertex, right. So if I take this vertex, then these 3 edges also get covered, and now I have something at the bottom. So I could take, for instance, this vertex and cover this. So now if I take these 3 vertices, then between them they cover all the edges. Now some edges can be covered multiple times, that's not a problem. I just want to make sure that every edge is covered. So if you imagine, for instance, that these are stretches of road and you want to put a camera at an intersection, and that camera can actually swivel around and scan all the roads which meet at that intersection, then what we are asking is, where should I put the camera so the minimum number of cameras are used, and yet I'm able to watch the traffic on all the roads in my network, right. So this is a typical example of finding. So I want, in this case, I want the smallest vertex cover, not the largest independent set in the earlier case, the smallest vertex cover, right. And again, here for instance, one small vertex cover is 1, 2, 6 and 7. So a checking version of this problem is there a vertex cover of size k? Right? Again, if I give you a set of vertices, you can check if it's a vertex cover, but is it the smallest one? Then you have to do some work. So these two problems appear to be similar. Are they connected? Well, actually yes. right? You can show that if U is an independent set and it has some size k, then its complement, the set of vertices minus U, is a vertex cover of size n minus k. So why is this the case? Well, if I look at the forward direction, so supposing U is an independent set, right, then you know that every edge has to be at most having one endpoint in U because it's an independent set. There are no edges between the vertices in the set. So every edge has one endpoint outside the set. In other words, outside the set, the complement covers every edge. So the complement is actually a vertex cover. Conversely, if I have a vertex cover, right, then we know that every edge has one endpoint in that vertex cover. So if I look at any two vertices outside the vertex cover, there cannot be an edge between them, because if there was an edge between them, one endpoint of the edge must be in the vertex cover. So there can be no edges between them, so the complement forms an independent set. Right? So this basically says that independent set and vertex cover both reduce to each other. So we saw last time that we can use reductions in two ways, right? Either we can translate an efficient solution for B into an efficient solution for A, or we can argue that if there is no good solution for A, then there could not have been a good solution for B. So here we can say that both vertex cover and independent sets seem to be difficult problems because we have to go through all subsets of things to find good sets on both types, and they reduce to each other. So if I can solve one, I can solve the other, because we saw that every independent set generates a vertex cover as its complement, and every vertex cover generates an independent set as its complement. So if I want to find the largest independent set, it's equivalent to finding the smallest vertex cover and vice versa. Right? So these reduce to each other, right? So these are both, as it will turn out, difficult problems to solve, just like the other problems we have been looking at, like traveling salesman and Boolean satisfiability, but they are checkable if we put this constraint of k, and they are interreducible, right? If you can solve one, you can solve the other. So this is the basis of what we are going to look at next, this interrelatability of intractable problems.